Let's get this party started. So last class, we had what? Rotational kinematics. We went over notes. We went over the front part of the page, and I gave you maybe number 5 to do. I can't remember if we did that together or not, but then definitely the back side was due for homework. I did hear from a couple of people. The most popular asked about was number 7, which is asked about in the chat. So let's go through number 7, make sure we have a clear understanding of where we are so we can kind of get into what we're going to do next. So that was the homework in all of its glory. We can scroll up to, let's see, we go up to number 7. Perfect. Zooming in so we can all kind of get an idea of what it looks like. We have a chef spinning pizza dough with an angular acceleration of 2 radians per second squared. Well, that's our alpha, okay? Like we've done this whole time, like we do, even in on level, I'm constantly telling them, AP on level, I don't care, you're solving problems. When you can, when appropriate, which is most of the time, find a place and write down the things the question gives you. It simplifies things, it isolates everything to one area, reduces the number of words, you get ready to solve a problem. So we have an acceleration, we have an alpha equal to 2. How many radians? So we're looking for theta. Theta is measured in radians, so we're theta. And then after 10 seconds, how many radians? The time is 10 seconds. Okay, give me a second. Let me adjust my my role based on letting someone in. Hold on real quick for me. Sorry for the interruption. All right, now let's get back to work. Okay, so we've got this bit of information. Now, in kinematics, we know, well, we know this is kinematics because the title of the document, right? The title of the document tells us that we're in kinematics. In kinematics, we need 4 variables, 3 that we know, 1 that we're looking for. So if it's 3 that we know, if we look at our list there in the margin, we only know 2. We need to determine what we know of a third. So if we're looking for a third variable, let's see even what the other variables are. Well, we've got acceleration, we've got displacement, we've got time. Well, the only things we're missing are the initial angular velocity and the final angular velocity. We need to know one of those 2 to solve this problem. Okay, well, once the pizza chef is spinning the pizza dough and it's accelerating for 10 seconds, how fast is it going then? We don't know that. Okay, well, what about the initial velocity? When the pizza chef walked up, was Luigi there in the kitchen already throwing the dough? Well, it didn't say that. So we got to imagine that the pizza dough was not spinning before the chef got there, that he's starting it from rest and starts to spin it. So that is one variable. Then come in and say, okay, the initial velocity is 0. And we can use that with some bit of, feel pretty good about using that. I can't hear you. Well, for somebody can't hear. All right, let me ask you this. Can other people hear me? Give me a thumbs up or thumbs down. Can you hear mine? Okay, at least one person put their thumb up. So everybody's, Caleb, can you hear me? Yeah, see, he can hear me. All right, so check your volume if you can't hear me. If you can't hear me, turn up your volume. Okay, there you go. To find final velocity, what I did was, okay, but right now it's not asking for final velocity just yet. Let's see, I can hear, let's see. Let me just type back to this person. Okay, now, final velocity, yeah, we might get to that in a minute, but from what we have right now, we don't need final velocity because we can assume the initial velocity was 0. Now we have 3 variables that we know, 1 that we're solving for. This allows us then to go into our kinematic equations and do some work. Let me move my notebook over where I can actually see what I'm doing. And my kinematic equation then would be theta is equal to initial velocity, angular velocity, times time, plus 1/2 acceleration times time squared. Well, we know the initial velocity was 0, so this part kind of goes away, that's 0. So then theta would be equal to 1/2 times acceleration of 2 times time, which is 10 squared, So theta is equal to 100 radians. We have 100 radians going on right there. Someone asked me, how is the initial velocity 0? Before the pizza chef spun the dough, was it moving? That's where I'm getting the 0 from. The pizza dough is not going to spin unless the chef is spinning it. It's lazy like that. So yeah, I mean, sometimes we just have to break it down and say, okay, look, I need one more variable. Let me list the variables I don't know and see if there's any assumptions I can make. And that's what I did with it. That's absolutely what I did with it. And there was only one that I can make an assumption about, and that was it. All right, let's look at how many times does the dough spun around in this time period. So how many times has the dough spun around? Every time it spins around, that's a revolution. So it's asking us how many revolutions did it go through during this time period. So we found theta in A. Now we want to convert theta to revolutions. We've got 100 radian. And we know that if radian's in the top, we've got to put it in the bottom to cancel it out. So I'm going to put radian down here. And we want revolutions. We know one revolution is 2 pi radian. Here, radians cancel out. If I take 100 and divide it by 2 pi. Now, do not put it in your calculator as 100 divided by 2 pi, because your calculator will think you mean 100 divided by, that's percent. What am I doing? Let's clean that bit up. Your calculator will think what you're doing is 100 divided by 2, and then it will say times pi. If you're going to put it all as one sentence in your calculator, use parentheses. You have to bracket it off. I'll type it in mine, 100 divided by 2, enter, divided by pi, enter. You just need to make sure it divides by pi. Okay, it keeps you from messing up. But once we do the math correctly, we should get their answer of 15.92, and our remaining unit is revolutions. That's what B is asking for. That's what B is asking for. Now on C, what is the dough's angular velocity after 5 seconds? This is asking for your omega, which is your final angular velocity. Okay. Here, we're going to change the time to 5 seconds, but outside of that, the acceleration is still valid. We've got final angular velocity is equal to initial angular velocity plus what? Alpha times time, something like that. So we would have final angular velocity is equal to, initial is 0, so we can put the 0 in if you like, plus 2, which is the acceleration, times 5, which is the time. So then that would equal to be 10 radian seconds. That's supposed to be a 10. That's the same solution they came up with. Again, this is just kinematics, but for rotation, for turning, where we're changing the variables in order to match. So, what's up?
Watley.
Yes, sir.
For part C, could you use the kinematic equation that has like 2a times the change in theta? Because that also, you can also use that to solve for the velocity.
You know, there's a lot of times that you can use variations. And even with the kinematic equations, if you've got more and more variables, it gives you more flexibility. I chose this one because I didn't have to rearrange it to solve for final velocity. And it seemed to be, in my mind, the simplest to do. But certainly there's more than one way to do it. And when you see those other ways, if you find that they're easier and shorter, hold on to those and keep those. I mean, that's the people that are most successful in math are the ones that discover their own shortcuts, understand them, and apply them. And everybody else around them's like, I don't get it. So yeah, if you've got other ways, if other things apply, absolutely. And yes, there's more than one way to get to the solution. Will this recording be available for reviewing? Yes, this particular class will be the one that I convert. It does take like a little over an hour spread apart. There's like a 3-step process. So I'll get it uploaded this evening, hopefully not very late, but yes, this recording will be up. That doesn't mean you can't pay attention right now. So I'm watching you. I saw who texted that. I'm just kidding, I'm not watching you, but you should pay attention live and then just use it as supporting material, right? Yeah, make me feel good. Okay, so that was C. That goes into Now, yes, there was not a solution for 8, or 8 is not listed for us. I'll give you the lowest to the highest. It was A, C, B. And what you need to do is do a kinematic equation for each of those, come up with a solution, and you'll see that they're in that order. Indicate the equations that support your reasoning. That's how you actually get it done. You use a kinematic equation for each one. You solve for angular acceleration, and then you'll see which one has the smallest to the largest. But the order that I got was ACB, ACB. If you really want to know, let me just give you what I got for each of the angular accelerations to make sure that you get something similar. So for this one, I got about 1.23. For this one, I got 1.48. And for this one, I got about 1.35. Or hold on. Yeah, 1.35. Those are the values that I was able to get through using kinematic equations through the practice. I want you to kind of go through the practice as well. Let's see, did you need to do a kinematic equation? I just did alpha equals omega final minus omega initial divided by time. That is a kinematic equation. The alpha equals omega final minus omega initial divided by time. Come up to my equation right here. Wait, which one is that one for? Alpha. Like if I took this equation right here, couldn't I subtract omega initial? So if I did this minus omega initial would equal alpha times time, divide both sides by, how did you do it? Divide by time, yeah, divide by time. And I would have, so that is, no, it's totally fine. And that's funny what you put in the chat. But the person was saying, hey, this is the equation I used. Couldn't I have used that? And I was just showing them that that is derived from a kinematic equation. Sometimes you don't realize that, you know, by rearranging those kinematic equations, you come up with things that you use all the time. But that's kind of how the kinematic equations came about, right? Things that make sense, and then it's just solved for a particular variable. No worries there at all. All right, let's stop the share on the homework. Stop the share there. Let's take a look at what we're going to be doing. So if I share from this screen, it would help if I had something to share. Let's see. There we go. All right, so this day in history, we did, so last class we did the, oh, look at what we're doing next week. We've got a quiz on Wednesday. So quiz on Wednesday with FRQ. We've got some warm-up stuff and some practice problems we're going to be doing on Monday. If I back up 1 week, and let's see where, this is where we are today. We're going to go over some notes for rotational inertia, moment of inertia. Then we're going to do some practice together, and then I'm going to leave the last sheet of homework for you guys to work on in the remaining time of class and between now and next class. When we get into Friday, it's going to be a little bit less intense on Friday, where we do torque at angles. It's not that bad. I think today is going to be the heaviest lifting, and then after that, it's going to be just kind of learning through the problems. So let's stop the share from here. Let's flip back over and start doing some of the work and getting through some of the notes. So I'm going to start with notes, and then we'll go from there. The notes really don't take that long. It is a bit of a discussion. It can be a little bit dry, but stick with me. If you see me write something down, or if I say something more than twice, it's probably somewhat important, but you choose. I'm going to take 5 pages of notes that I have in front of me, and I'm going to turn them into half a page for you. So I'm going to try to hit the high points so that you don't have to decide what the high points really are. All right, so let's get this party started. Pick that color. We're good to go there. All right, rotational inertia. Rotational inertia is also called what? What did I say it was on the title? Moment of inertia?
Inertia, yeah.
Yeah. So what do we know about inertia? Let's go back to when we were talking about mass at the very beginning. We had mass, and we said that mass has a resistance to change in motion, right? Every object that at rest wants to stay at rest. Every object in motion wants to stay in motion unless an external, unbalanced external force acts on it. Doesn't that sound really like Newton's first law? Kind of, we went from kinematics, now we're going to Newton's laws. So really, that's kind of inertia is what? It's a resistance to what?
Change in motion.
Well, change in motion, but I want one word. What's one word for change in motion?
Displacement.
How about acceleration? Because you could be moving already, but you don't want to slow down or speed up. You could be at rest and you don't want to change. Acceleration is really what's happening. When a force is applied, you get an acceleration. Without that force, you just want to keep doing what you're doing. So really, mass has a resistance to acceleration. That's why you need a force in order to create that acceleration. So that resistance to acceleration, up to this point, we've treated all masses as point masses, okay? Or a point in space. We didn't care what it was. In kinematics, we didn't care about the size. We'd either say, hey, the masses are canceled out, or mass isn't in the equation. Why are we worried about mass? Well, mass didn't matter till now. I mean, it has a little bit, but now it really does. The shape even matters when it comes to rotation. So let me write this down. We had rotational inertia. It's also called moment of inertia. You may see it different ways in tests. I'll probably gravitate towards rotational inertia because it makes the most amount of sense to me when I hear the word rotational inertia compared to a moment of inertia. All right, so we've got rotation. See, rotation, yeah, that's right, rotation, all inertia. Okay, so if inertia is a resistance to change in motion, what's rotational inertia?
Resistance to change in rotation?
Okay, I like it, but I don't like using the same word that's in the definition as what's you're defining. So you're right there, but I'm just going to use a slightly different term because I don't like to use its own word. Yeah, and I see it in the chat too. So I'm going to read what came up in the chat. Resistance to change angular motion. It's a resistance to change your angular motion. Let's write that down. Resistance to change angular motion. Ran out of room on that line, but it fits in, no problem. So when you twist an object or you move it in a circle, sometimes you'll notice that there's some sluggishness, like it doesn't want to turn or doesn't want to rotate, and that object is hard to twist. Let's use a baseball bat as an example. Most people, if not have picked up a baseball bat, they can imagine a baseball bat. And if you grab a baseball bat, so they're long, right? And you grab it, normally, where would you grab it if you wanted to twist it back and forth? Where would you want to grab that baseball bat? Now, so somebody said the handle, but are you doing it like down at the bottom where the knob is? Or are you doing it up towards the middle of the handle? Because the baseball bat has a really long handle where the rabbit is. Yeah, I would grab it towards the middle. Now, why would you grab it towards the middle? I agree with you, but why would you choose the middle?
Because if you grab it at the middle, then because in a baseball bat, right, there's more mass at the top than at the bottom.
You're right, but let's channel the 7-year-old self inside you. Why does the 7-year-old, when they're playing with the bat and twirling it, why do they grab it from the middle? Because they're not thinking about the mass.
It's easier to balance it.
Yeah, it's easier, and that's where it balances from. It's so much easier if you grab it from the knob, which is at the very end, that kind of round part. If you grab it from there and try to twist it back and forth, you're going to hurt your wrist. I mean, that or you're going to be really strong, but it would hurt my wrist trying to take a heavy baseball bat and twist it there. But if I do it in the middle, it's really, really easy. So the shape is important, but the distribution of the mass is important. And we see that without even thinking about it. If you were to spin your table, if you were to spin your pencil on your table, that center part of the pencil that it's spinning from, the part that looks like it's not really moving, that's where the center of mass is located, because objects want to spin from their center of mass. If you roll a ball across the floor and you look at it in profile where it's coming from your left to your right, how it's rotating, that center part that it's rotating around, that's where the center of mass is located. Now, as long as you're not putting an axle through something and causing it to rotate at a certain location, objects want to rotate around their center of mass. All right, so then let's talk about rotational inertia again. What does rotational inertia depend on?
Angular acceleration.
I mean, that's part of the equation ish. No, no, let's give me something else. So if I'm going to take that baseball bat or any other object and I want to look at its rotational inertia, how much it resists the movement, what are some very simple things, two things I'm looking for that it depends on?
Mass.
Mass is one of them. So here, let me write this down real quick. Depends
Contact.
on, number one, mass. And number two, what was that again?
Point of contact.
Yes, but I'm going to use different words. You're absolutely right. But I'm going to say it in physics terms now. So instead of our 7-year-old brain self, let's back up to where we are and let's say, okay, well, point of contact, what does he mean by point of contact, or can we put it in different words? What if we were to say that it's how far the mass is from where your point of contact is, or the distribution of mass based on where you're pivoting it? Okay, so you're right, it is point of contact, but it's point of contact in relation to the mass itself. So let me write it down in that way. So it's how far that mass is from the pivot. All right, and then we got to ask ourselves, what is the pivot? Pivot is the point of rotation for an object or a system. We talked about how an object wants to pivot around or rotate around its center of mass. That point at which it's pivoting is the pivot. All right, that point at which it's rotating is the pivot. Something simple, most of you look like you're in a room that has a door nearby. If you were to open your door, it swings in a circular motion and it pivots at the hinge, that point at which the door is attached to the wall, to the door casing. So the pivot for a door would be the hinge because that's where it's moving from, okay? I hope it makes a little bit of sense. If not, that's okay. It's a long class. You'll catch up. Let's look at the formula itself. So if we were to take that and turn it into a formula, we can say that it is, I don't know, we called it I. I is going to be our rotational inertia. It's equal to mass times the distance to the pivot squared. So rotational inertia, that's the I. Mass is the M. And then the distance to pivot. That's the R. So the rotational inertia of a point mass around a pivot is just saying that for a point mass, for just any mass, any little object that we've reduced it down to a point, the rotational inertia, or the resistance to change your angular motion, is equal to the mass times the distance. As the mass goes up, we can see the rotational inertia increases. As the distance that the mass is from the pivot point, the rotational inertia will increase. That's going to be one of your big ideas, is increasing the mass or the distance to the pivot. Either one is going to increase your rotational inertia, which is your desire to not change. The difficulty in making a change. The bigger the mass, the harder it is to turn it, okay? So let's look at a couple of examples. I'm going to scroll this up so that we can see a little bit more of the screen. I'm going to keep the formula on for now. And let's get, I have 5 examples. Okay, the first one is going to be a stick with a pivot at the end of the stick. And I'm going to compare that to a stick with the pivot at center. That was supposed to be an at sign. It didn't come out very well. All right, so then here's my stick. There's the pivot. Let's call the pivot right there. And then here's my stick. Let's put the pivot right there. Let's say that that's the center right there. So one is grabbing the baseball from the knob, One is grabbing the baseball bat from the center, saying, okay, it's pivoting there at the center. Okay, now we're going to take our formula and we've got to adapt our formula depending on the shape of our object in the mass distribution of our object. So our natural formula, our raw formula, our starting formula is I equals mr squared. But if we've got a stick or we've got a shaft or we've got a board and we're pivoting it from the end, our formula becomes I is equal to 1/3 m. Now here there's not a radius, it's more of a length. So it's going to be ml squared. The distance, instead of being a radius, it's a length, we use L. I know, it's confusing. It wasn't my choice, but it is what it is. Now from the center, now the mass distribution is better. It's closer to the center than it was in the beginning. So if the mass distribution is closer to the center, that means our calculation for the rotational inertia should be less. It's got to get smaller. Already we were doing 1/3 ml squared. And if this is going to get smaller, that means we're going to have another fraction. So here it's going to be I equals 1/12 ml squared. I know, it's confusing, it sucks. But
Wait, Mr. Watley, I have a question.
what's that?
How are you getting the coefficients on the right side of the equations for the rotational inertias?
You mean the 1/12 and the 1/3?
Yeah.
I'm giving them to you. I'm not calculating them. I'm telling you what they are.
Okay.
These are like known values. I'll tell you this, in your homework, you're going to have your notebook open and you're going to be able to pull the equation from your notebook. During tests, it'll either be listed or you'll have your notebook open where you can refer back to your formulas. When you get to the AP1 exam, they will always tell you what the rotational inertia equation is for that problem. So it's not something you have to memorize, but it's something that you have to become accustomed to.
Mr. Watley, like, are those the only 3 points we'll have, or like, will there be more points?
I've got 3 more for you.
Okay, thank you.
No problem. It's kind of like, do you have to? Can we just stop there? But no, we can't stop there. All right. So
Sorry.
what's
What I meant is will there be like will they just give us like a random spot like on the question?
Oh, no. It's most things are going to be based on the center, except for this one that's like a baseball bat where you're grabbing it down from the bottom and it's pivoting from the outside edge. The other 3 examples we have are circular, and they're all based on the pivot point being in the center.
Okay, thank you.
Absolutely. So everything's really going to fall between these 5 things that I'm going to give you. I've given you the first 2. Let's do the other 3. So I'm going to scroll this up. And now let's look at a ring. Okay. A ring being the mass is on the outside. And let's do like a line in here. So the ring, sort of like a donut. Fill that in. So it's like my wedding ring. I'm going to hold it up to the camera. So all the mass in my wedding ring is on the outside. It's as far from the pivot point as possible. There's no mass near the pivot point. Everything is on the far outside. So in this case, the mass is getting as far away as possible. So it's increasing what the rotational inertia is by the mass's distribution. Here will be a favorite because I equals mr squared. Simple. It's just simply I equals mr squared for a ring. Now, what if that ring is filled in? A filled in ring is also called, here, let me give a title. This is ring. Well, a filled in ring where it's flat on each side, that is a disk. So this is my version of a disk. Now we've brought more of the mass towards the center. We're going to imagine the amount of mass in the ring is the same as the disk. We've just smushed it and moved all those atoms, all those molecules, a lot of them closer to the center. Instead of being real compact and dense on the outside, now it's distributed nice and even from the middle to the outside edge. So now we know that compared to the ring, we're going to have less of our rotational inertia. In that case, our formula is going to be I equals 1/2 mr squared. The very last one, I can't draw a 3-dimensional circular shape. I'm just not that good. So I'll just give it the name sphere. And for a sphere, now the mass is distributed even better around the center of rotation because it can come all the way in 3 dimensions instead of just out to the sides. And we've got I is equal to 2/5 mr squared. What's important to me when I'm doing these problems, I note in my notebook, or I make a notation in my notebook where these equations are so I can find it easy. If you've got a highlighter, highlight them. Put an asterisk in the margin or whatever, so that when you're going through the problems, you can flip back and find this. That to me is what's really helpful. So now we've taken 2 pages of notes, well, essentially 3 pages of notes. We're done with those, only have 1 little page left. And realistically, it's not much to that. So it's something we just need to know. Something you need to know how to access and to work, but you don't have to memorize. You need to understand why they're different because it's the distribution of mass. And you need to know how to execute the problems, but you don't need to memorize. Yeah, you're wondering about the numbers in front of the M, the fractions. Yeah, I made a joke earlier today and said, well, I went to Home Depot and I got a lot of lumber and I made a lot of cuts and I did a lot of experiments and I came up with these numbers. But realistically, it's just 7 out of 8 physicists agree that these are the right numbers. The 8th one couldn't get a job, so, we don't count that one. Yes, it says 2/5. And yes, that was a joke about the lumber and the 7 out of 8 physicists. But these are just known values based on experimental design and coming up with fractions. It's kind of like you never asked me how come it on the kinematics equation that's 1/2 AT squared. Like, well, why the half? It's like, oh no, it's the equation. It's on the formula chart. So there you go. All right, so that's kind of get through this. Let's get through one last idea and then we'll kind of get into the work a little bit. I mean, ish. All right, so let's get through this last idea. I'm gonna scroll this up. We talked about, I'll scroll it up to that point at least. Now we talked about Newton's first law, right? So what comes after Newton's first law?
Newton's second law.
Look at that. Why is it always okay, at least I got somebody in chat too keeping up. It's like, why is it always not the IHS students that are answering my questions? I control the chat. Yeah, you do. All right, so let's do this. Newton's second law, we said was summation of forces. Yeah, that's my summation sign today. It's a little weird, but that's my summation of forces. That's equal to mass times acceleration because forces accelerate. And this is talking about linear motion. Forces accelerate things. You have an unbalanced force, your object is accelerated linearly, okay? But we're talking about rotation. So here we're gonna say, when we go to angular motion, we're gonna say that torques twist. Torques twist. Or we can say cause alpha, which is angular acceleration. Angular acceleration is speeding up or slowing down in a twist or a turn. Here we can create our formula then and say, well, the summation of torques, and that's a Greek tau. So I have the epsilon and then the tau. I know it looks like a crooked C with a top on it, but that's like a tau, a Greek tau is equal to rotational inertia times angular acceleration. Torque, or the summation of torque in a system, is equal to the rotational inertia times angular acceleration. Now, torque is a force applied to an object to cause a twist. Torque is a force applied to an object to cause a twist. In a more simpler form, we could have even said that torque is equal to force times displacement. If we were talking different ways to look at the same thing. Okay, that gets us some formulas. That gets us through the notes that I had written out that I want to make sure that I covered. The next thing I want to, go ahead, what's up?
Would the displacement be like the radius or in radians?
It'd be the distance in meters from the pivot point to the place where the force was applied.
Okay.
Is the squiggly T the torque? Yes, the squiggly T is the torque. I'll circle it in red. So this is torque, which is torque. Yeah, that's squiggly T. And it's called a Greek tau. It's like T-A-U or T-U-A. Here, I had it written down. Let me see. T-A-U, the first way I wrote it down, T-A-U. That's how you, that's what the word is. Like, you know, the squiggly E is the epsilon. Well, that's a tau. At least so I've been told. I'm just trying to organize my notes. That takes us from my handwritten notes to our actual page that has notes and a couple practice problems. We're going to do these problems sort of together. Oh. Okay, so I just closed my Chrome out. It's going to take me just a second to open it back up. Anyway, let's do a couple of these practice problems together. We'll get through it, and then I'll turn it over for homework. So open from computer. So I'm going to go to the rotation 2 page that's in our Canvas, and we're going to fill in that chart. Now, if you like to open it up and fill it in together, if you like to write it down, if you like to print it, print really fast, and we'll be ready to go, because now I've opened it up, and I'm going to share that screen. All right, let's do this page together. I promise it'll take what seems like forever. Promise. Okay, so let's take a look at this. Let's give a name to each of the of these quantities that they've listed for us. So I know it's called theta, but ultimately, what is it really? It's angular displacement. And I'm using abbreviations, A and G for angular, DISP for displacement, angular displacement. That means the omega is angular velocity. The alpha would be angular acceleration. The I we learned today is rotational inertia. And the T there is torque. Okay, so just giving some names to the things. All right, I think I've caught up all that stuff. Okay, the linear analog. So when we were talking about linear point to point, and when we talked about displacement, the character that we used was X. For velocity was V, acceleration was A. For rotational inertia, what was the linear analog? What do you think?
Mass.
Yes, mass. What about torque?
Force. So
Yeah.
F.
Yes, absolutely. All right, now for the next column, formula linear to rotational. I gave you some of these last class where I said, how did I put it? Like X equals R times theta. Well, let's just rearrange it so I give you the same thing, but it's just presented a little bit different, where I can say theta then is equal to X over R. We can say that omega is equal to V over R. That's just equals. Alpha is equal to the change in W over R. Let's see, is that what I wanted? No, I'm looking at the wrong thing. Hold on. Got a little bit ahead of
Shouldn't it be A or alpha equals A over R? Yeah.
Yeah, the next one over, my eyes shifted to the other column. I'm looking at my cheat sheet to see how I wanted these written, and I looked at the wrong column. For this one, we didn't really have a linear relational formula for that one, but for torque, we have torque is equal to force times displacement. Now, if we were to go through the next column for other formulas, this first one.
Wait, so Mr. Watley.
Yeah, what's up?
So for saying force times displacement, would that be different from the R before?
This is for torque, when we say R times force, this R is saying how far from the pivot is the force applied. Not where before we were looking at when we were looking at the 1/2 mr square or mr square, that R is the total width of the system. This is where the force is being applied to. It's a small designation, it's a small difference, but if I had a wrench and I apply my force at the midway point, my R would be the midway point. It wouldn't be the entire radius. If you've got a disc, then you can only apply it to the outside edge because you can't get to the middle of the disk. If it's like filled in, you're coming from the outside. But for torque, it's where the force is applied and how far is that force from the pivot point. If we go to the formula other part, this one I don't think I've ever really used, but theta is equal to, we know 2 pi is 360 degrees. So pi then would be 180 degrees. So one that I don't ever use, but okay. I've got omega is equal to change in theta over time, change in theta over time. I've got alpha is then equal to change in omega over time. We know that I equals mr squared, and we know that torque is equal to I alpha. The units on these, at least the top 3, you're going to know immediately. We know that theta is in terms of radians. We know that omega is in terms of radians per second. We know that alpha is radians per second squared. That brings us to the I. What is the R in torque formula? The R in the torque formula is the distance from the pivot that the force is applied. The distance from the pivot that the force is applied, that's torque, no problem. Let's see, we've got those units. The last 2, if it's m times r squared, that would be kg times meters squared. And then for torque, we would have Newton meters, Newton times meters.
Would it be Newton meters or? Oh, it would because you have. Oh yeah, okay. I got it.
Force and distance, yeah. All right, short descriptions. I like short descriptions. So the first one with theta, we're just going to say that it's the number of radians an object turns through. So number of radians, object turns. There should be an N, turns through. All right. For omega, that's the velocity of rotation. For alpha, let's call it the acceleration for a rotating object. Acceleration of rotation. Now, rotational inertia, I'm just going to call it rotational sluggishness. It's just a resistance to rotate. So it's sluggishness, it's desire to fight it. And then for torque, we're going to just say creates a twist. You can also think leverage on that one, if you think about leverage. All right, this is a good handy chart that you can refer back to as well. It's also kind of distinctive in your notes, so it's easy to find. All right, let's go through these questions and let's make sure we have enough time to get through them. If you need to, take a screenshot of this, refer back to the video, whatever works for you. But the information here is going to be valuable as we're going through these questions. I'm going to scroll up and start looking at number 2. Describe 2 things that affect the rotational inertia of an object. How do they affect the rotational inertia of the object? So what are the 2 things that affect the rotational inertia of an object?
Mass and distance.
Mass and distance. And if I increase the mass, what happens to rotational inertia?
It increases.
What about the distance? If I increase the distance, what happens to rotational inertia?
It increases.
Increases, absolutely. So we have mass. The more mass, more inertia. We have distance from the pivot. More distance, more inertia. All right, so it's very straightforward, and it comes directly from the formula. So no big mysteries there. Let's scroll this up. Now we've got a picture. All right, so let me draw with, well, red works. So this red line is kind of where it's pivoting. Okay, that system is pivoting. On the left side, I have a mass of 2m, that is a distance from the pivot of L. On the right, I have a mass of m, that is a distance of 2L. And it's rotating about this. So first thing is they want us to find the inertia of each mass. So somebody tell me, what is the inertia of each mass? 1, 2, 3, go.
So for I guess mass m, would it be m times 4L squared?
That's the rotational inertia. What is the inertia?
M?
All right, on the right, I would have m. On the left, I would have 2m. Remember, inertia is mass. So if it asks you for inertia, it's asking you for the mass. It's kind of a trick question, right? We've said before, inertia is mass, and if it says find the inertia of each mass, it's saying find the mass. What are the masses? It's a crazy question, but yeah, I've got 2 people in the chat that gave it to me, 2m and m, and then another person put m and 2m. Exactly right. Now it says find the rotational inertia of each mass, and here I'll tell you rotational inertia. We can say that I equals mr squared. So what's the rotational inertia of the m?
M times 4L squared.
Yep.
Or, yeah,
4L squared. I'm good. What's the other one?
2ML squared.
Sounds good to me. We basically took the mass and we squared the distance. So those are the 2 rotational inertias, one for each mass that are going about that pivot point. We just solved that equation for those 2. We know the distance, one is L, one is 2L. We know the masses, one is 2m, one is m. Mass times distance squared. That's all. So far, that is all. So now it says, does the mass with the greatest inertia have the greatest rotational inertia? So does the biggest mass have the biggest rotational inertia?
No,
Why?
because when it comes to rotational inertia, the length, the distance matters more as it's squared.
She's exactly right. The smaller mass has a rotational inertia of, allow me to rearrange the variables. The smaller mass, the one that is just m, its rotational inertia we calculated is 4ml squared, where the 2m, twice as big, has a rotational inertia of 2ml squared. So the distance does play a bigger role. It is squared. And you can't just go to the increased mass. It means increase the rotational inertia. Yeah, but increased distance is squared. So you got to do the calculation to make the comparison. So the answer is no. And the y is what we just talked about. Okay, the y is what we just talked about. Going into the very last one on this page, it says find the total inertia. That's the first half of the equation. First half of the question. I'm going to scroll this up just a little bit. There. What's the total inertia?
3m.
3m. Yep. He was able to do that by saying, well, one side has 2m, the other side has 1m. Total inertia would be inertia plus inertia, 3m. And the rotational inertia of the system. Okay, rotational inertia, again, is I, and it's for the system. So the total I, or we can say the system's I, is going to be equal to I1 plus I2, on and on and on for any of the rotational inertias that we have. Well, we said that we had 2ml square, and we had a 4ml square. So the total system's inertia would be 6ml squared. Make sense? Can I explain C again? Yes. It says, does the mass with the greatest inertia, which means the largest mass, have the greatest rotational inertia? Let's look at B. The smaller mass has a rotational inertia of 4ml squared. That's the small one. The larger mass has a rotational inertia of 2ml squared. Well, the smaller mass, 4ml squared, is bigger than the large mass of 2ml squared. So in this case, because the distance is squared and it has the smaller one has a larger distance, it then had the larger rotational inertia. And we showed that between A and B. Your answers in A and B indicate your answer for C. Could you please repeat how I equals mr squared becomes? Okay, so someone's saying, could I repeat how? Okay, so I equals mr squared. What is the, for the small mass, what's the mass? It's m, isn't it? Okay, so we have m. Then r squared. What's the distance that m is from the pivot point in the picture? It's 2L. Well, what's 2L squared? 2 becomes 4, L becomes L squared. And then for the smaller mass, oh, that is the smaller mass. For the larger mass, the mass is 2m. So our formula is mr squared. The mass is 2m in the picture. And then its distance squared would be, in the picture it says the distance is L. So L squared. I'm going to circle part of this and draw it to it. So I'm going to do this, do it in red. This part right here goes to that. And this one right here goes to this. Okay, I don't mind stopping and even backing up and doing this. I want to make sure everybody is understanding this. It's at times can be a very tough topic. In my opinion, today is the hardest day of the year. Understanding this and getting a good grasp on this, to me, this is when I say rotation is the hardest, that's today. We get through today, it gets easier. And if you've already got it, that's great. It's going to get a little bit more challenging today. So just let's get through the rest of this lecture and see where we are. But I don't mind answering questions. All right, so let's go to page 2, which is the back side of this one. All right, now we've got a picture. We have R1 that is, well, here we have two cylinders. The bigger cylinder has a thread wrapped around it, and from that thread is dangling M2. So here's M2 down here at the bottom. It's hanging off of a thread on the front side of a big cylinder. Then there's a smaller cylinder to the left that has a thread wrapped around it, and on the back side hangs M1. They do give us the radius of the two cylinders, and these two cylinders are stuck together, gorilla glued, okay? They're not gonna slip from one another. They're totally adhered to each other, but they can freely rotate on that axle that's drawn through them. So I'm going to read through the question. Let's see what all it says. Two masses, M1 and M2, are connected by light cables. That just means that light cables means we don't have to factor in the weight of the cable. That's why I called it a thread. To the perimeters of two cylinders of radius R1 and or radii R1 and R2. The cylinders are rigidly connected, gorilla glued, to each other, but they're free to rotate without friction on the common axle. So they can spin all day long, but they're gonna, if one turns, the other turns. They are stuck together. All right, so now let's look at the questions. If the mass of the small front cylinder is 10 kilograms, what is its moment of inertia? All right, well, a cylinder is just like a disc, and we said that I equals 1/2 mr squared for a disc. Pretty sure. At least that's what I wrote down. So then we would have I equals 1/2 times the mass. They said the mass is 10 times the radius squared. In the picture, it tells us the radius is 0.5, and that is to be squared. When I did the math, I got 1.25 kilograms times meters squared. Just plugging in the information directly from the picture, from the description. We want to know what is the moment of inertia, which is the rotational inertia, same thing, for the front cylinder. Now we have to do the same thing for the back cylinder. I do have to scroll a little bit. We'll start losing the picture here in a minute, but we still know that I equals 1/2 mr squared. So then I would equal 1/2 times the mass of 40 times the radius. They told us the radius was 1.5 squared. That radius is in the picture. That's what I got it from. We know the equation is 1/2 because a cylinder like this is most like a disc. In your notes, the disc, remember, it's not round like a sphere. It's not hollow like a ring. It's completely filled in, but it's flat on the two sides. So now when we do this math, I got I equals, I want to say it was 40, yeah, 45. 45 kilograms times meters square. So now we've gotten the rotational inertia or the moment of inertia for the two cylinders. Okay. Now if we scroll up to C, what is the total moment of inertia? Here, remember the I total is equal to I1 plus I2, that sort of thing. So we just have to sum them together. 1.25 plus 45 equals 46.25 kilograms meters square. Just adding them together. We calculated them. We're cool like that. All right, we got A, B, C. All right, D. D's the last one. It's also the worst one. Oh. All right, they're telling us, basically, look, let's go back to the picture. It's going to tell us that the mass of M1 is 20 kilograms. And it's saying, what does the mass of M2 have to be so that this system is in equilibrium? Meaning it's not going to turn, meaning it's balanced, meaning it's chill and happy. So in order for it to be chill and happy, what has to be equal to each other?
The forces that are acting on the system.
All right, I love your answer, but I want you to be more specific. What is an angular force?
Displacement time.
We said force is our linear terminology. Yes, it's in the chat. Someone say it out loud though.
Torque?
Torque, it's torque. Our torques have to be equal. So yes, it is a force, but it's a force causing us to turn at an angle or a twisting motion. So if the torque going to the back is same as the torque coming to the front, if those torques are balanced, it's not going to turn because it's balanced, it's happy, net torque would be 0. So let's write that down. Let's come back up here and let's start figuring this out. So in order for the net torque would be torque 1 minus torque 2 equals 0. That's what we want for equilibrium. If I add torque 2 to the other side, we'd basically have torque 1 equal to torque 2. Because equilibrium means you subtract them and you get 0. So then if we add torque 2 to the other side, that just basically means their magnitude, regardless of their direction, their magnitudes have to be the same. One's positive, one's negative, and they're balancing each other out. So then let's go back to our sheets, our formulas, the table from the last page. And torque was, what is torque again? How do we calculate torque in terms of angular measurements?
IA.
IA. So that means IA, or I alpha, has to equal I alpha. For number 1 has to equal for number 2. And then what did we say I was? I is merely mr squared, isn't it? When we're talking about torque, we're just talking about a force applied to rotate something. We don't care what it is. And if we don't care what it is, we just go to our natural formula, which is mr squared, right? So that means that m1 r1 squared times alpha has to equal m2 r2 squared times alpha, right? We're just breaking apart what I is. And if we really want to get fancy, and we kind of do, what's alpha?
0. Well, the net torque is supposed to be 0, so alpha is 0.
Look at your chart. Look at your chart. Come on, man. Look at the chart. How can we define alpha?
Oh, angular velocity over time.
I would like the one that says A over R. Do you see the A over R?
Oh yeah, linear acceleration over radius.
Let's do that. And now each one of these has its own radius. So what we're going to have is m1 r1 squared times acceleration A over r1 is equal to m2 r2 squared times A over R2. Now those squares will take care of the radius at the bottom of the fraction. Let me circle them in a different color so we can see what I'm talking about. Let's go with like yellow. This square can take care of that part of the fraction, that square, because we're basically saying times R2 divided by R2. So we can simplify it. Now there's one other thing that I want to simplify. That is the acceleration. What is the source of the acceleration?
The torque.
Work.
No. This is the object dangling from the cylinder. What
Gravity.
Gravity. So that means those A's are really G's. Those A's are really lowercase g's. Those accelerations are merely the accelerations based on gravity pulling them down. So that means, I'm gonna change my color to black because now we're starting to get serious. And let's move this up here. So we would have M1R1 times G is equal to M2R2 times G. Here, we've simplified the square by getting rid of the denominator on both sides. And we said, well, the acceleration is gravity. See, I told you this is about to, the crap's going to hit the fan. We're like, wait, what? Told you. It's not, this is the one, you got to stick with me through these. They're hard. All right, G's cancel out. They show up on both sides. So that means M1R1 is equal to M2R2. We're trying to solve for M2, so let's divide both sides by R2. And we end up with, that should be an R. Let's move this over here. We have M1R1 divided by R2 is equal to M2. Now, M1, they told us is 20 kilograms. R1 is 0.5, it's in the picture. R2 is 1.5, it's in the picture. When we take 20 times 0.5 divided by 1.5, when I did that, I got 6.67 kg equals M2. I know.
Mr. Watley,
Yes, sir.
why couldn't you cancel like angular acceleration before we broke it into linear acceleration over radius?
Because when it was alpha, it was on one side I was dealing with R1, on the other side I was dealing with R2, so it wasn't the same.
Oh, okay. Okay.
Mr. Motley,
Yes, ma'am.
couldn't we just like use the rotational inertia formula for a disk and then set it equal to each other, like for mass 1 and mass 2?
There it wouldn't have made a difference because you would have had the 1/2 on both sides and that would have canceled out. But then as we get to other problems with torque, when we're converting out of torque, we're just keeping it as mr squared. So you won't always be able to cancel it out and be okay. When we're looking at torque on these problems, we don't need the number in front is not what's important. If we were calculating the rotational inertia for a certain object, then we look at its shape. But when we're just applying the torque, we're not looking at the shape. We're just applying a torque.
Thank you.
I know it's confusing. That's why this particular unit, this particular lecture of the unit is like the worst of the year, because even the kids that get things, the students that get things really quickly, all of a sudden they get frustrated because it's not as easy as it normally is. Not that it's ever really easy. I mean, let's be honest. Okay, let's scroll this up. All we have is number 5, and we're about out of time. All right, luckily number 5 is the last one, totally the last one. All right, so what do we have with number 5? I'm going to take their picture and I'm going to draw my own a little bit. So what do we have? We have a beam that's, let's see, a rod. Okay, rod of negligible mass, meaning we don't care what its size is. So here's my rod, and I've got a mass right here. I've got a mass right here. That's a mass of M. This is a mass of M. Okay, and then there's a rotation of the axis right here in the middle. Okay, and then I have a bug that comes up. Let me move that M to right here. Then a bug of mass M3 comes flying up. So This is 3m. And it's going to land on that left side of the rod. Now they told us the whole rod is 2L, so that means this side is L and this side is L. Now when that bug lands on the left side, it's going to cause the system to rotate in a counterclockwise motion, right? At least right at first, the bug lands and it's going to cause the system to rotate. So when that rotation happens, the rotation would look like it's going to come around and go this way. So our angular acceleration is going to be in that direction. Does that make sense to everybody? Bug lands on the left side's going to dip, and it's going to twirl that way, at least initially. Now after that, when the bug starts going up, it's going to end up pendulum-ish motion, but let's not worry about that. Let's just talk about what's going to happen in the beginning. All right, now that we have an understanding of what's going on, let's take a look at the questions and see if we can answer these right away. Find the total rotational inertia of the system. Total rotational inertia of the system. Okay, well, we know that I equals mr squared. Okay, that's the formula we're going to use for this one. The total inertia is going to be I total equals I1 plus I2 plus I3. There's 3 masses here, and we're going to look at mass times radius square. Well, the bug, let's just calculate this together. The bug has a 3m mass, 3m, and then we have to square the distance. The distance is L, so that would be L squared. Now the mass, that little knob on the end, that's just m. So, and then its distance is L squared. And on the other side, we have m and L squared. So all together, we've got 5mL squared. Does that make sense to everybody? That's all we get. Is it fine we don't completely understand this right now? Yes, because you've got the video to review back. The homework will help because you don't really, if you fully understood right now, you'd never have to do the homework. Doing the homework, working the problems, it's going to help things click. As long as what it sounds, as long as it doesn't sound like I'm speaking a different language right now, then I would worry. Why is there another 2mL? Because there's a mass on the left and a mass on the right. There's 2 masses. So what if I numbered them in the diagram? I've got 1 and then 2. So I'll mark this one 1 and 2. Wouldn't it have a 1/12 since it is a rod with a pivot in the middle? This is a rod of negligible mass. Since it's negligible mass, we don't have to do the 1/12. The 1/12 would be as if we had like a rod that has a mass and we're worried about the distribution of the mass from the pivot point. Here, it's a negligible mass. The rod is of negligible mass, so we don't have to. Again, it's one of those like, why, what, I don't get it. I know. I get that you don't get it. I mean, I've been there before. All right, let's look at this a little bit further. Find the torque from each mass and the bug. Okay, so let's talk about what torque is again, and let's further confuse everybody. Not intentionally, it's going to happen that way. So over here on the right column, I hope you can see my right column. I'm going to say that torque is equal to I alpha, right? And we said that I is mr squared, and we said that alpha is merely A over R. Well, the square takes out the denominator, so that leaves me with mRA. And we said that, let me put the equals, and we said that the A is really G, is really gravity.
Should we just memorize this conversion? That way we don't have to do it for every problem.
Yeah, but since I gave you like 17,000 formulas today, I don't want to use the word memorize. But if you can see where it came from, then you don't have to memorize. But yeah, if you can see where it came from and you just know it, it's not going to hurt you. But for those that want to stab you for saying I have to memorize something, I'm not going to hand out your address, so don't worry about it. That was a joke. No one wants to do that. I'm sorry if that was a joke in poor taste, but hey, I'm old. All right, so let's see. Find the torque from each mass and the bug. All right, so let's do it one at a time. We got the bug. All right, we said that it's mRg. Okay, so mass would be 3m. The radius is L, and G is still just G. Okay, for M1, is just simply going to be mlg. And for m2, again, it's mlg. Well, that's not too bad, right? I mean, if we can break down torque into mrg, we can apply that for each of these things based on their mass and their distance from the center, that sort of thing. We've got it. We're almost done. We're at C. Sweet. We're going to beat the bell. All right. What is the net torque of the system? All right. So the net torque, let's see if I can draw this, is equal to the torque 1 plus the torque 2 plus the torque of 3. That's the bug M1, M2, right? Now, this is one part that's tricky, and I don't want it to surpass you. We see that the system wants to go this way, right? It's going to go this way. It wants to go this way, right? So 3M and M on the left side, they're going the direction they want to go, right? But what about this M2? Gravity says, hey, buddy, you want to go this way, but it's being forced the opposite direction. Its torque is pushing down, but the system is making it go up. So it's not helping the system move, it's fighting the system. And I get it, be rebellious, fight the system. Come on, power to the people, right? That was meant as a joke. Come on, Kylie, smile. Bigger than that. There she goes, see? All right, now, if it's going in the opposite direction, that means it's not gonna have the same sign. So we could make the bug positive 3 mlg plus the mass on the left, which was mlg, but then we have to subtract the one that's opposing them, mlg, and that equals 3 mlg. That is the torque on the system, the net torque. Because the one on the right is not helping the system, you can't add it to it. It's opposing it. It's going in the opposite direction, or it's trying to. So its torque has to be subtracted from the net torque. This is just like with the Atwoods, where we had objects hanging on either side, and depending on the direction of the system, its mg would either be added or subtracted from the net force on that system. Same thing here. Same thing here. All right, if we're good with that, we can finish this up with something that's not quite as bad. I think C is like the worst. But anyway, D, let's look at D. What is the initial angular acceleration of the system? All right, well, here I want to go back to the torque formula, because torque was equal to I alpha. And if I rearrange this, I could say that alpha is equal to torque divided by rotational inertia. And the reason I want to do that is it's asking me about the system. So I need to know the information about the system. Well, guess what? The system's torque was calculated in C. The system's rotational inertia was calculated in A. We've already calculated those two values. And if we divide those two values, we get the system's angular acceleration. Let's put those numbers in. 3 mlg divided by 5 ml squared. The m's cancel out. The square on the bottom takes care of the L on the top, and I'm left with 3g over 5L. And that is the angular acceleration of this system. And that completes this page. And oh my gosh, don't you want to just stop and take a nap? I kind of do, but hey. All right, I'll leave this up on the screen for a second so that you can get all the way caught up. There is a homework page that is not nearly as intense, but it has challenges of its own.